You ever stop and wonder how we measure something we can't see or touch or hear? Well, today we're going to unlock a really cool puzzle in physics. How a physical law itself gives us the tool to measure one of nature's most powerful, invisible forces. So, yeah, let's pull back the curtain on this.
So here's the big question, right? We can all feel a magnet's pull. We know it's there. But how do you actually put a number on it? How do we measure its strength? Turns out the answer is hiding in plain sight, right inside one single foundational equation.
And this is it. This is the key we're looking for, the Lorentz Force Law. Think of it like a master recipe. It tells you the total force that a charged particle is going to feel. It covers how both electric and magnetic fields mess with it. And somewhere inside this blueprint, we're going to find everything we need. So let's break down the ingredients.
First up, you've got F. This is the total electromagnetic push or pull on our little particle. It's the effect, the thing we can actually see and measure. We use a unit called the Newton for this. And just to give you a feel for it, 1 Newton is, well, it's roughly the force you feel from gravity holding a small apple in your hand.
Okay, next ingredient, Q. This is simply the electric charge of the particle itself, and we measure it in coulombs. You can just think of a coulomb as a standard packet of electric charge. Is it a proton, an electron? The bigger the charge, the bigger the force it's going to feel. Simple as that.
Then we have V, and that stands for velocity. Now this part is absolutely crucial. For the magnetic part of the force to do anything at all, the charge has to be moving. A charge that's just sitting still, it doesn't feel a thing from a magnetic field.
The equation also has an E in it. That's the surrounding electric field. This is the force that would act on the charge even if it were just standing still. So you can think of it as the first half of this whole electromagnetic puzzle. And finally, we get to the one we've been hunting for, B. This letter, B, represents the magnetic field itself. It's right there in the formula. But to actually define it, we've got to figure out a way to isolate it from everything else.
So, how do we do that? Well, it's pretty clever. We can just set up our experiment in a place where there's no electric field. We basically just set E to 0 in our equation. And by doing that, we've stripped down the recipe to only the magnetic parts. And look what happens. With that electric field gone, the law becomes just beautiful. The force is now just the charge times its velocity interacting with the magnetic field. This relationship is our key. It tells us exactly how a magnetic field pushes or pulls on a charge that's on the move. Now here's the really elegant part. If we set things up just right, so the particle moves perpendicular to the field to get the max force, the equation becomes simple multiplication. And now, with just a little bit of basic algebra, we can shuffle things around to get B all by itself. And voila! We've just defined the magnetic field using things we can actually go out and measure: force, charge, and velocity.
And this is where the magic really happens. See, an equation isn't just theory on a page, it's a practical tool. Because the units on one side have to balance out the units on the other, this simple formula gives us a precise recipe for creating our unit of measurement. Okay, so let's check out this table and see how it all stacks up. Based on our formula, the units for B are newtons per coulomb meter per second. Yeah, I know, it looks kind of messy, right? But watch this. A coulomb per second, well, that's the very definition of an ampere, the unit for electric current. So we can simplify this whole thing down to newtons per ampere meter. And this specific combo of units gets its very own special name, the Tesla. And there it is. That's our payoff. We have a concrete physical definition built right from our experiment. 1 Tesla is the strength of a magnetic field that pushes with 1 Newton of force on 1 coulomb of charge moving at 1 meter per second. The law didn't just describe the relationship. It literally created the ruler we use to measure it. How cool is that?
So from now on, when you see 1 Tesla, don't just see a unit. I want you to see the whole story packed inside it. A specific force acting on a specific charge, moving at a specific speed. It's a whole physical definition, all wrapped up in a single word. This quote here really sums it all up perfectly. The Lorentz Force Law isn't just some principle you memorize from a textbook, it's what's called an operational definition. It literally gives you the operation, the actual procedure for how we go out into the real world and measure a magnetic field. Once you see it this way, it kind of changes how you look at everything. The Newton, the volt, the watt.
They aren't just random names. They are physical laws packaged into a single word. So the next time you see any unit of